Okay, so we're going to talk about recursion both this morning and this afternoon. Much like objects and higher order functions and arrays, we'll be spending two sections on it. Let's hear about this a little bit. For the most part, the morning session and the problems you do in the morning will probably be more alike what you will see on the assessments or the interviews. And it's a little bit more kind of not entry level, but it's a little bit more basic. In the afternoon sessions, we're also going to be talking about recursion, but that kind of probably a little bit more complex beyond what you would likely see on the interview. So we're going to tackle the afternoon session a little bit differently than we do the morning session. Do you want lights on or off?
Can we do off? Does anyone else want
on? I felt like them off yesterday made me more
tired. Okay.
Never mind. I was just kidding.
Cool. Well, if not, the bagels will do the same thing probably. Okay.
Wait, do you think we can keep that fan on or something though?
It's really loud. I'll try to make this lecture really fast, so it'll be 20 minutes tops of cool. All right. Are you right? You look really tired. Are you right?
I got like no sleep last night. Yeah, I'm good though. You got it.
Okay. Cool. All right, let's power through it. Okay, cool. So recursion one. So recursion. We're going to kind of do a few concepts that will set up the idea of recursion. Everyone kind of has heard of recursion as, it's a function that calls itself, which is definitely true, but it's also a bit of an oversimplification. And if you just think about it that way, it's most helpful, but I can also lead you some pretty dark path. For this morning session, one of the common things you'll realize is, hey, all these problems that we're doing with recursion, we can do with a for loop, and that's absolutely correct. For everything we see this morning, we are able to do these problems with recursion, but we're also able to do with a for loop. This afternoon, we'll see a certain class of problems that you can only do with recursion and not with for loops, right? So with this morning, it's less of a look at what makes recursion unique, but more like, hey, let's try to understand recursion at its basics, and let's also put it in context or a comparison to something that hopefully you're a lot more familiar with, right, with a for loop. So for the problems today in the workshop for this morning session, yes, you are able to do all those problems probably a lot more easily and a lot more comfortably with for loops, but obviously please use recursion because the point of this session is not to do these problems, but really is to learn different concepts. In the real world, people use recursion because, quite honestly, while it does have its kind of sharp edges, it actually so on one hand, it will solve certain problems that you can't solve iteratively, as you can't solve it with for loops, or at least not very easily. But the other thing is when you use recursion, it also kind of breaks a problem down into a very, very simple level. I know you've heard me harp on this a lot over the past week, but with recursion, you really what recursion really does is it really kind of makes you focus your thinking and get a really clear understanding of what problem it's solving. And usually when you look at a recursive problem, you realize that what we're really doing is we're not solving a massive problem, we're just solving a very simple problem over and over and over again. And so that's kind of like one of the hallmarks of recursion is, hey, if we can take this seemingly onerous, very complex thing and just break into a very simple problem, and we just do that, and we're doing it for a finite number of times, recursion really shines in that context. And so we'll see a few examples of why that is. Okay, so we can't talk about recursion without talking about the call stack. I'm sure I'm recording right now. Yep. Yeah, so we can't talk about recursion without talking about the call stack. The call stack is something that's very, very critical because the call stack really is, for a computer, is kind of really what determines their priority level. When you think of a call stack, think of it as like a to-do list for a computer. A call stack basically tells a computer, hey, you're working on this. After you're done with this, we have a list for you to do next, right? And computers, obviously, maybe they're not like humans. They don't just kind of pick around and cherry pick the ones they want to do first here and there. They have to do it in the order that the call stack is created in. So if you know a computer's call stack, then you know kind of definitively how a computer is going to execute. This is also why when I talk about code, I always say, make sure you know what the computer is going to execute next, right? Because a computer doesn't just kind of pick what it wants at any given moment. A computer has a call stack, and so as a programmer, it's up to you at any moment to know kind of what's coming up on your computer's call stack, to know what line of code is going to execute next, or even which code you're currently executing. JavaScript is single threaded, and what that just basically means is JavaScript can only do one thing at a time, and it can't do the next thing until it finishes this thing, right? So in most cases, it will never say, hey, like this looks really hard. Let me skip this for now and let me come back to it later on, right? It will say, yeah, you want me to do this next? Great, I will keep doing this, and if I never finish, if I never reach into this, I'm just never going to finish. I'll never reach in, even if there's other tasks after me. On one hand, this causes a lot of dangers, like when we use a while loop that never ends, right? Your computer just kind of crashes, or your computer kind of burns out because it does the same thing infinite times. On the other hand, it's very critical to us, right? Because when we define a variable, then we use it in the next line. Our assumption is, hey, we're not going to use it in the next line until we finish defining it first, right? And so because of that, like this direct linear approach forms a lot of the basis for how we write code. Okay, so the way to think about a call stack, you can think of it however you want. I think the most common way people think about it is it's like if you ever been to a buffet and you have a stack of plates. They're waiting for you to take the plate and get some food. The call stack is kind of like a stack of plates, right? So what does that mean? If there's 5 plates there, right, and I just did dishes and I washed one dish, I come over and I put it on that stack of plates. Where is that plate now? At the top, right? It's like the first, quote unquote, the first plate. And so if someone else was coming over to get food, they're like, oh, hey, let me grab a plate. Which plate would they grab? The top, the one that I just washed, right? So this is something called last in, first out, and it's I mean, the name is fairly descriptive, I think, and what it basically means is the last thing that comes in automatically becomes the most important thing or the next thing that gets processed in JavaScript. So we're going to see a few examples of how that works too. Okay, so when we talk about a call stack, here we have 2 functions. One's called first, one's called second. When I execute it, what happens is the call stack basically keeps track of what the computer is working on at that moment, right? And remember, a computer can't move on to the next line of code until the first line finishes. So here, when I look at this code we have here, lines 5 through 12, we're defining functions, but nothing's running, so it doesn't quite matter just yet what they do. On line 13 is the first time we actually run a function, right? We run the first function. And so when I do, on my call stack, guess what? The first function kind of pops up, right? Like that's on my current to-do list. And what does it mean? So then what does it mean for line 14 to run? What has to happen before the second function can run? Right, first has to finish, right? Line 13 running first and line 14 running second means second cannot run until first finishes. So on line 13, when I invoke my first function, on the call stack, the first function is on there, and now the computer will say, great, hold everything else, I need to finish first before I do anything else. So how do I finish first? I jump back to line 5, I look, okay, what am I doing for first? I am console logging out I am first. Everybody good so far? After a console logs out I am first, what does it do? What else needs to happen in the first function? Nothing, right? I reach the end of my code block. Remember, functions in JavaScript can only end one of 2 ways. Either we get to the end of our code block and there's no more code to run. Either JavaScript says, "Hey, I'm done. I'm gonna return undefined," or we use a return statement to end it, earlier or prematurely, or end it somewhere else in the block, right? So a function can only end in one of those 2 ways. It's always going to either end with an explicit return statement, or it's going to finish running all of that code and be like, cool, I have nothing else to do, right? You gave me a list of things to do. I did all of them. I'm done with the list. I'm moving on. Okay. So after we console log out I am first, the first function is now done. And so when it goes back, when we look back at our call stack, the computer basically says, oh, great, I was working on the first function, but now I'm done with it. So guess what? I can tick it off, right? I can take it off my to-do list, and now my call stack is empty again. And only when it's empty do I say, all right, great, let me move on to the next line of code, which is what? Second, line 14, right? All I've done so far is I finished line 13. I'm now finishing line. I'm now starting to tackle line 14. I run the second function. Great. So in order to finish up this part of the call stack, I need to finish up the second function. So I console log out I am second, and then I've reached the end of the second function code block, right? So my second function is also over. My call stack is now empty. The computer says, okay, great. I just finished line 14. What's next? no other code. This page of code is done. So the computer says, okay, great, I can move on now. Like I finished, right? So whenever you run your code, whether it be in CodePen or Repo or anywhere else, that's the exact sequence that happens, right? The computer goes through your line of code one by one, and it will tackle each thing one at a time. And when it reaches the end of the page, it will be done. So this is why when I ask you to walk me through your code, I always try to say, be as explicit as possible, because this is what the computer does, right? The computer is going to read through it line by line by line by line. It's not going to skip over certain lines. It's not going to kind of abstract out ideas. It will mechanically go through it line by line. So if you're not able to do that with your code, then you're probably going to have some conflict with your computer. Okay. Now let's look at another example, right? So this looks so the second function is identical in the first and the other slide, right? It still console logs out I am second. But now when we look at the first function, what does it do? It console logs out I am first, it invokes second, and then it console logs out first is finished. So if we were to run this function, let's talk about how this will look in the call stack. Okay. One, between lines 1 through 10, is anything being invoked? Well, so in order for line 3 to be invoked, what has to happen?
You have to invoke the function unlocked.
Right, you have to invoke the first function, right? And so between line 10, between lines 1 through 10, if first is never being invoked, then therefore nothing inside first is ever being invoked either, right? So between lines 1 through 10, nothing is just being called, right? We're just literally defining a bunch of variables here. We're defining a first and a second variable, and then both functions. That's all we know. Okay. Line 11 is kind of where the action actually kicks off. We start invoking our first function. And per usual, we add the first function to our call stack, right? This is now priority number 1 on our to-do list. So the computer doesn't even need to know what's on lines 12, 13, and 14 just yet, because it knows that it can't move on to those lines until it finishes first, right? So at this point, I'm just saying, let me just tackle first. Let me get this done. Okay, let's go inside our first function. The first thing we do in the first function is we console log out I am first. Great, so far so good, nothing fancy. The next thing we do is we have to do, so now we get back to Hisei's comment on line 3. Now we're invoking the second function. So what does that mean? This means now we have something else we need to do, which is invoke the second function. And more importantly, what does running second mean? Running second means until we finish running the second function, we can't do what? We can't finish the first function, right? The first function goes lines 2, 3, and 4, which means we need to run line 2, line 3, and line 4. Well, if line 3 never finishes, we can't ever go to line 4 just arbitrarily, right? We can't just skip the rest of line 3. So now this is the instance in which your call stack builds up, right? So now we have the first function on our call stack here, but now because of line 3, we're putting the second function on top of the first function, right? We can't wipe out the first function because guess what? We never finished it yet, right? We're still in the middle of finishing the first function. But as a prerequisite, as a requirement for finishing the first function, we have to run this second function. And so now, second function becomes like the new plate I just put on the stack. Like it's like the latest, shiniest, cleanest plate. I put it on the stack. Well, what does that also mean? Right. This means that this now becomes my latest priority, right? If I'm if I'm a patron to the buffet, I come by now. This becomes the next plate that I take, right? To a computer, this is now the task that's on the top of the queue. So this automatically becomes the next thing that it finishes. Okay. So great. The computer says, okay, well, in order to finish first, I have to run second. So let me tackle running second. Well, so when we run second, we go to line 7, and then we go down line 8. Line 8 just console logs out I am second. So we do that. And after we run that, are we done with the second function?
Yes.
Yeah, we're done with it, right? We've reached line 8. We're at the end of the code block for the second function. So now at this point, because we're done with second, we can actually take second off of our call stack. Okay. Once we take second off our call stack, what does that mean? It means we've now finished the second function, right? We finished line 3. So now this gives us permission to continue on where we left off, and we can see them in both places, right? After we finish second, we resume back to what our original task was, which was the first function. And when we look at the code order, right, we finish invoking second, So where does that take us to next? After what next line does it take us to? It takes us to line 4, right? Where we left off. And so now we're on line 4, which makes sense because our call stack says we're still working on this first function here. We finished console log out first is we console log out first is finished. And then finally we finish the first function. We finish the first function and we take it off our call stack. Right? So this is where the call stack is important because it kind of lets you know what, not detours, but kind of what other things you're going to prioritize in the middle, right? So just to walk through this again, we only invoke first once on like the global scope, if you will, right? We invoke the first function, it console logs, then it says, all right, in order to finish me, you have to do this other thing first, right? If you play like video games or adventure games, this is like a side quest, right? Or not even a side quest, it's like a prerequisite quest. It's like in order to get this prize, you have to do this first, right? So therefore, in order to finish first, we have to run second. After we run second, we then can move on to the next line. First, pick up where we left off, and we say, great, the last thing I got to do is I got to console log out first is finished, and now I'm done with first, and I'm done with the whole page. Notice how after I finish running second, right, I don't restart from first from the top again, right? I just basically said I execute this line of code, and then I'm moving on to the next line, okay? So remember, after you kind of do that detour, you don't pick up from the beginning, you pick up where you left off, right? Otherwise, this would create an infinite loop, basically. So after you run the second function, you then move on to the next line from where you were at. Does this make sense? Okay. So far, no recursion yet, right? This is just an idea of kind of helping you understand how and in what orders functions execute. Okay? Cool. All right. So now let's take a look at a very simple problem, right? We want to write a function that counts down from whatever number we give it down to 1. Okay. So in this problem here, in this solution here, we have a countdown. We have a problem called countdown. We have a function called countdown. It takes in a number, and it looks like all we're doing is console logging that number from that number all the way down to 1, right? And so here we're using a very simple for loop, right? Hopefully this point is like kind of table stakes for us, right? All we're doing is we start at I equals num, as long as I is greater than or equal to 1, and as long as every iteration we're decreasing I by 1, we just console log out I, right? So we start at 5, work all the way down to I equals 0, at which point we stop, except we never console log out I equals 0 because I equals 0 violates our condition in the middle of the for loop, right? So this is a problem that, quite honestly, looks pretty simple and makes a lot of sense when we do it with the for loop. But because we want to make things a little bit harder, let's do this recursively. Okay, so this is kind of the main problem where so in this problem, the idea here is, okay, what really are we asking our function to do here, right? Like, what's like the mini problem, right? When we use a for loop, what we're doing is we're actually planning out kind of all 5 iterations of the loop, right? And we're saying, hey, I know I'm gonna need to do this, x times or 5 times. Let me have a loop or a for loop, and I plan this out in a certain way so that I control all 5 iterations, right? But when I'm only looking at things one number at a time, at its core, all I'm really doing is I'm just printing out a number, right? You give me a number, I print it out. That's pretty much it, right? So if we have that as our function here, so here we have a function called countdown, and it takes a number, and all it does is print out a number, we can also write this problem this way, right? Countdown 5, 4, 3, 2, 1. Obviously, super inefficient, a lot of typing, but it works, right? Like, this also gets the job done. It's just not very, very, very flexible. But this kind of brings us to this nice kind of, I guess, idea, if you will, which is that, hey, look at this. Countdown never changes, right? We always call countdown. The only thing that changes is what?
Value?
Yeah, it's the argument. It's the value. It's what we feed into the function, right? So how do we actually change or is there a better way for us to change the argument between the calls? And this is where recursion and so this is where what the for loop was doing for us earlier kind of really comes into play, right? What the for loop was really doing is it was calling the same console.logout. The only thing it was really doing differently for us was between each call, it would have an I variable and it would subtract 1 from it, right? And then check to see if it violated the condition. So what if I had a function myself that did the same exact thing, right? I take in a number, I print out the number, and then I call myself with that number minus 1. Okay? So here, when I have countdown of 5, I'm going to do 5, console log out 5, and then I'm going to call a countdown of 5 minus 1, which is 4. And now I'm starting to kind of mimic this idea that, hey, I can call myself over and over again, except every time I call myself, I get smaller by 1, right? So I'm doing conceptually the same thing as a for loop, where I'm decreasing by 1, but now I don't really need a for loop, right? And in fact, at every iteration, I don't care what happens. Like, I don't care what happened before me, and I definitely don't care what happens. Like, I only care enough to trigger the next run. I don't care about anything after that. When you write a for loop, you care about all the runs at once, right? You're kind of playing God in the sense that you have control over all 5 runs. Here, you just have control over yourself, and really whether or how you trigger the next iteration. That's it, right? So if you think about a function as kind of like a problem, like the scope of the problem just got very, very small, right? You care about what you do with yourself, and you care about whether or not you kind of kick off the next process or how you kick off the next process. That's it. You don't need to think about all 5 processes. So when we run this code now, what's going to happen is we're going to have our call stack, which is countdown of 5. Cool. And then countdown of 5, the first thing that's going to happen is we're going to say console log out num. Console log out num, which is console log out 5. And then we're going to do countdown of 5 minus 1, which is countdown 4. Well, guess what? Has countdown of 5 finished yet at this point? It hasn't, right? What has to happen before countdown 5 can finish? We have to finish running countdown 4 before countdown 5 can finish, right? And so that means countdown 4 now gets added to our call stack. Everyone see that? And so in fact, I'll draw it out here because this is a concept that like I think like visually makes a little bit more sense, which is a lot of times when people think, so I'll call this countdown of 5 here. I have my code, right? When I have countdown of 5 here, a lot of folks think that what a lot of folks kind of tend to think is like, oh great, when I get to countdown of 4, I'm running the same function again, except I'm like changing this to a 4, right? But really that's not what I'm doing. What I'm actually doing is, I have my console log out of 5, and here I call countdown of 4, right? This is just simplification of this function here, right? What this is doing is, this is actually triggering another function call. And what function call is it triggering? Countdown 4. And this will console log out 4, and what will this do? Countdown 3. So then this will trigger another function call called countdown of 3. Okay, so I mean I'm not gonna obviously finish this because this is a small board, but countdown of 2. But if you notice, like kind of like in this very like hasty drawn like chart here, right? Like the point here is that I'm not just kind of like countdown of 5 running this over and over again. Each time I call countdown, I'm invoking a new instance of the function, right? So this function is, for all intents and purposes, it's completely separate. Countdown 4 is almost completely separate from countdown 5. You see that, right? And so when I call countdown 3, I'm creating a new function that's also running, but countdown 3 is separate from countdown 4, right? All the variables that exist in countdown 5, do they exist in countdown 4? Assuming here I had a variable that was like, let x equals 3, would this x variable exist inside here?
Yeah. No.
Well, we'd do it again and say let.
Right. So
that x would.
okay. So well, actually, like I guess like what I'm doing kind of wrong here is in this function here, right? I'll put it like back as a comment. Num is equal to what? 5, right? What is num equal to here? Right? So maybe this is a better example. They both had num variables, right? But whenever I count down 4, I'm not using the variables that exist in countdown 5 and just kind of replacing one number. I'm creating a brand new function call, and this function call is completely separate from the previous call, right? This has its own processes, and it has its own value for what the variable num is. Okay, so the big takeaway here is that, once again, we're not like changing one number inside this and then kind of doing everything to this function. We invoke a brand new function. Everything gets created from scratch. It's almost like these are just two different functions, right? Like if this function was called like Davis function, and Davis function calls countdown, well, I wouldn't expect them to be the same thing, right? Similarly, even though they're named the same thing, I'm calling it twice. So the first time I call it, I have these set of variables in this process. The next time I call it, this is now, you can think of it as like a brand new scope, right? This has its own processes, its own variables, and is completely separate from this. The only link between these two functions really is whatever I return here is going to get returned here, because this is what called me. But other than that, everything else is completely separate, right? So when I look at the call stack now here, when I ran countdown 5, and it calls countdown 4, I'm not running countdown. I'm not staying in countdown 5 and saying, oh, num is now 4. I'm running countdown function all over again from scratch, creating a new instance of it, and in that instance, num is equal to 4, right? And so every time we see one of these things, one extra plate on the call stack, that's one of those. It's an extra brand new process, right? It's, I guess, to use kind of a disgusting analogy, right? Like at a buffet line when I have a new plate, right? I'm not just wiping off the same plate for you over and over again, right? I'm actually putting a new plate on there, and a new plate on there, a new plate on there. Same thing here. Every time I put a new plate on, it's a brand new thing. It's a brand new function call. Okay? Yeah.
How does it know when to end?
Great question, and we will spend the next 30 minutes talking about that. Anywho, so let's just kind of take this down to the wire, down to the end of the right? Oh, look, okay, countdown 4 is going to call countdown 3, countdown 3 is going to call countdown 2, countdown 2 is going to call countdown 1, and then here we see Megan's problem, which is, hey, look, we're just going to keep going, right? And we never, ever stop. And so clearly at some point, what's going to happen here?
The computer's going to crash.
Computer's going to crash, infinite loop, but now we can actually talk about it in a little bit more detail, which is not just the computer explodes, right? But really what causes the computer to explode? You have way too many tasks going on at once for the computer to handle, right? And remember, if I was to type all of these out manually, say run countdown, let's say my countdown function was only a console log, I could run all of these in sequence super easily, right? I can say log out 1, log out 2, log out 3, all the way to like a billion. The computer will handle it totally fine. But here, it's different, right? Because here, by the time I get to countdown of -2, what's happening to countdown 5? It's still running, right? So the computer is not just saying, hey, I can't like print out 20 or 15 numbers in a row. The computer is saying is, hey, you're asking me to kind of maintain this memory of countdown 5 while maintaining countdown memory of 4, while maintaining countdown 3, and so on, right? And so my computer's memory can only hold so many things simultaneously. And so this is where infinite loops get really, or rather in this case, here's where this infinite loop gets really dangerous, is because we actually exhaust the computer's memory, right? A computer can can handle one task, finish it, next task, finish it, next task, finish it, really infinitely, right? But if you say, here's a trillion tasks at once, which says, hey, look, I have a capacity, right? I can only handle so many things simultaneously. And so that's why our computer kind of crashes, or we burn, or something bad happens, or our program freezes, right? Like that's the reason why. It's because when we use recursion poorly, we actually hold too many things simultaneously, right? Because those functions are all running still. By the time we get to countdown -1 million, countdown 5 is still like, hey, like hopefully I get done soon, right? But as of right now, I'm still going because I'm waiting for countdown 4 to finish. And countdown 4 is like, well, I can't finish until countdown 3 finishes, and so you kind of create this really vicious cycle. So yeah, maximum call stack size exceeded. That's one error that you will see probably if you do this. Okay, so then the question is, and Megan's point kind of summarizes this very well. It's like, Okay, so when do we stop, right? Like we've now figured out a process to keep going really well, but when do we terminate? And so the question now becomes, when do we terminate? Well, clearly we have to write something in our code that actually helps us terminate, right? So remember what we said about the mini problem that we were solving, that each function solved, which is, hey, all I'm worried about is myself and kicking off the next iteration, right? So if every single iteration, if every single instance of the function worries about that, well, once we reach, I guess, quote unquote, the end, in order for us to stop the function, all we have to do is what? Right? So if we think about it from the perspective of the function, right, with the for loop, we tell it when to stop, right? Like we're playing God, we're at a high level, we're saying stop at 0, right? If we zoom in and we're like a mic, and we're putting ourselves in the perspective of the function, the way to stop is to just not kick off the next iteration, right? Like the buck stops with you, right? Like, and so how that looks in code form is here. If you notice, this is still what we had before, right? Now we're just wrapping this in an if else block, and basically what we're saying is, hey, if num is less than 1, console log out done, and then what runs next in our code in this function after we run line 4. It's done, right? We console log out line 4. We already ran our if block, so our else block doesn't matter, right? Like whatever's in here does not matter at this point. Then we reach line 11, we're like, oh, we're at the end of our function, so therefore we're done with this function, right? So in this case now, we've kind of created a scenario where, hey, all we're saying is if num is less than 1, console log done, else keep doing the thing that we were doing before, which is console log out a number, and then kick off the next iteration. And so the crazy, like the really crazy kind of thing here, and why this works is, guess what? Every single time we call this function, we're doing the same exact check, right? So when console log of 5 runs, it'll basically say, hey, is 5 less than 1? No. Great, let's kick off, let's go to our else statement, let's console log out 5, and let's kick off countdown 4, right? And then the next thing what countdown 4 is going to do is countdown 4 is going to do the same exact check, right? Every function isn't worried about what the iteration before it did. It's not worried about like what the next iteration is even going to do, right? It's just worried about itself. And this is why recursion is different than iteration. In iteration, you pretty much need to consider everything all at once from the very beginning. You need to tell it, hey, you start here and you stop here. With recursion, you don't even plan that far ahead. You just need to make sure everyone knows their role, right? Everyone knows what they're doing, and you assume that if everyone's doing their job correctly, at the end of it, you will get done, right? So it's kind of like if you're a manager, right? Like one way to manage is to say, hey, like let me micromanage every single person and every single job that they do to make sure that I know it's coming together correctly. The other one is saying, hey, if everyone understands their role perfectly, and I just say go do your work, like by the end of it, it should finish theoretically like perfectly, right? So here, so going back to this example now, when you go to countdown 4, 4 is doing the same exact check, right? 4 is saying, I don't know what number you were before, I don't know what number you're afterwards, but all I know is right now I'm 4, and I need to check, am I less than 1? I'm not. Great, so let me go to my else statement. I console log out 4, and then I kick off countdown of 3. And 3 is going to do the same as a process, like, hey, I don't know what number you were before, I don't really care what number you are next. What am I? I'm 3. Am I less than 1? No, I'm not. So I go to my else statement, right? All the way until I get to num equals what?
1.
Nope.
Oh, 2 actually.
Nope.
0.
0. Right?
Oh yeah.
Is 1 less than 1? No. Great.
Okay,
So I'm going to keep going my else statement, right? But when I really violate my condition is when num equals 0. Is 0 less than 1? That's the first number in which I say, yeah, I'm less than 1. So then I console log out done, and guess what? I'm finished, right? I don't kick off any next iteration. I don't kick off countdown -1. And so when we look at this code here, right, when we get to countdown of 0 here, it's going to say console log out done. And at this point, what happens? Countdown of 0 is finished, right? I'm in my if block. My else block clearly does not matter at this point anymore because I already met the if condition. I reached line 11, which is the end of my code. And now countdown of 0 is finished, right? So we can easily just go back here and make this example a little bit simpler. Right, so let's just make this 0. This is going to console log out done. This is going to be 1, console log out 1, count down 0. And this is going to be 2, console log out 2, count down 1, right? So at this point, I've finished countdown of 0, right? Which basically means this whole function is finished, right? Notice how finishing this function has no impact on these other functions yet. Why? Because once again, they're distinct things, right? They're not like, oh, like I'm doing the same thing over again. They're distinct functions. They're distinct calls. So when I finish countdown of 0, I take countdown of 0 off my call stack. And so the next question becomes, okay, what was I doing before this, right? Like I took off the first clean plate. Someone else comes, they want to take the next clean plate. So what was I working on before this? Oh yeah, I was in the middle of finishing countdown of 1. And so if I finish countdown 0, what else do I need to do to finish countdown of 1?
Console log done.
Why console log done?
Because it's the last line in the function.
Where?
Line 4.
Well,
But one isn't less than one.
I needed to invoke countdown 0, right? So at what line do I invoke countdown 0?
Mm.
13.
Nope.
What line is countdown 0 invoked? Isn't it still 13?
No. Right. Countdown 0 is invoked on line 9, right? When num equals 1, countdown of 0 is being invoked, right? When num equals 1, is 1 less than 1? It's not, right? So we're not in our if block. So we go to our else block. We had console logged out 1, and then we had we invoke countdown of 1 minus 1, which is 0, right? So right now we're on line 9 essentially, right? And this code is saying, hey, I just finished running line 9. What do I need to do next? Nothing, right? Countdown of 1 is finished, right? And if there was another console log after this, we would run that, right? But the idea here is, at this point, all we want to do is we want to move on into the next line where we left off in countdown of 1. It just happens in this case that we've finished running countdown of 1, right? Yeah, Jake?
Wait, so does this just not end? Because now, like,
It's going to end.
number would be -1?
Why would it be -1?
Isn't it doing, like, 0 minus 1 right there?
Well, before, so now we're going back into countdown 0 land, right?
Right.
So let's run through this function line by line. Num equals 0. What's the first line that we hit?
Well, I guess.
Okay, so in general, JavaScript runs sequentially, right? After
Right,
line
so I
1
guess
is line
3.
2. Okay, so what's line 3 asking?
If 0 is greater than 1.
No.
I mean, if 0 is less than 1.
Is it?
I mean, yeah.
Yeah?
Oh, yeah, so it counts. Never mind. Okay.
You good?
Yeah.
Right? So we never hit this line,
Yeah, no,
At all.
Right, yeah.
right? We stop here.
Yeah.
Right? It's an if else block. We only do one of the 2 blocks. So if we console log out done, we're not going to kick off in the next iteration. If we kick off in the next iteration, we're never going to hit done. Okay? So back to where we left off under countdown of 1 now, right? We had invoked countdown of 0 here on line 9. We just finished that function. And as Megan said, there's nothing else for us to do in countdown of 1. So we can actually just say, okay, great. I've reached the end of countdown of 1. Let's cross this guy off. And now we can take this off our call stack because we're done with it. So that left us at where? Countdown 2. Is there anything else we need to do on countdown 2? Which line did we leave off at for countdown 2? Line 9, right? That's where we invoke countdown 2. And the question there is, great. Let's say line 9 is finished. Is there anything we need to do for that countdown function? No, it's at the end of the page, right? After line 9 is line 10, and then after line 10 is line 11, and the end of our function block. So clearly, there's nothing else for us to do there. So countdown 2 finishes, and then lastly, the problem. Now we're back to countdown 3. What was countdown 3 waiting on?
Everything else.
More explicitly, what was countdown 3 waiting on? What was countdown 3 waiting on?
Oh, call our function 2 to finish.
not callback, countdown function 2.
Yeah,
Just a
countdown
yeah.
function.
Yeah.
Sorry.
Yeah. So countdown 3 was waiting for countdown 2 to finish, right? So now that countdown of 2 finished, we go back to line 9. The line 9 for this iteration, just kind of bear with me, right? For this iteration of countdown of 3, if you will, right? We're on line 9. We were waiting to finish countdown 2. We finished countdown 2. What else needs to happen for countdown 3 to finish? We worked our way from 3, 2, 1, 0. And now we're working right back up 0, 1, 2, 3 because everything like countdown 3 was waiting on was finished. So now what does countdown 3 need to do next? Just finish, right? It's done. There's nothing else to run, right? We went from 3, 2, 1, 0 here. So when 0 finished, it allows us to finish countdown 1. When countdown 1 finished, it allows us to finish countdown 2. And when countdown 2 finished, it allows us to finish countdown 3. And that was our original call on line 13. So at this point, we say line 13 is finished. We look in our code block. There's no other code after line 13, so we're good here. So this page of code is done.
Is there going to be an example where there is more code that needs to be run, like for certain?
What do you mean there's more code that needs to run?
Like you were going back and you're like, okay, there's nothing else I have to do for countdown 2. Let's just continue. But if there is something that you need to do for countdown 2, is there going to be like an example showing?
Yeah, but at that point we're just running code normally.
Yeah.
Right? Like there's nothing like
So that would just be more code written underneath countdown -1.
Yep, there would be more code after line 9, between line 9 and line 10. We can add like 5 more console logs between line 9 and line 10 if we want, right? But it's just like it's gonna run before it finishes, right?
Yeah.
Like at some point, the whole point is just saying that like, hey, when we hit this guy, we can't move on to the next line until that function finishes. And that function is waiting on another function. Well, we're just it's kind of like a traffic jam, right? Like if the car in front of you is stuck, well, that car can't move until the car in front of that moves, right? And so you're just kind of stuck waiting for everything in the chain to finish. Okay, so basically, with a recursive function, the two most things are you're basically always faced with a very simple decision, right? Which is when do I stop and when do I go, right? When do I kick off the next iteration and when do I just say, hey, like I'm the last person, like I'm done here, right? And so what we call like the stop condition, we call the base case, right? So with any recursive function, you always need a base case. It's like a while loop, right? You always need a condition at which you're stopping. If your function has no base case, then it means it'll just keep going infinitely, and it will almost never be correct. Okay. So always have a base case, and when I look at your recursive functions during the workshops, the first thing I'll ask you probably is, what's your base case here? Like, when are you stopping? And then the second thing is, and this might sound very, very similar to what we talked about with the for loop and the while loop, which is, hey, whatever input you're changing back and forth, it should get you closer and closer and closer to your base case, right? You don't have to know exactly when you stop, right? It could be like rolling a die, right? You don't know when you get a 6, even. But the idea is like every iteration should theoretically be getting you closer and closer to your base case, so you are able to stop. All right, Josh.
Are if statements the only way to define a base case?
No. You can define it however you want, right? You can define it however you want. I mean, at that point, you're just writing JavaScript, right? You just need to like do something that does not trigger like the else call or the kickoff, right? Another way to think of the base case is, when do I not trigger the kickoff, right? Is there a way for me to avoid triggering the kickoff? That's pretty much it. Usually, it'll be wrapped in an if loop because it's the most convenient. But there's no inherent tie of like if loop to base case. So you can have a base case without an if loop, probably. If we think creatively enough, probably we'll come up with some way. Okay. Yep. So recursive functions also become a little bit more. They become a lot more complicated when return gets involved. Because so far, all we've done in the problem so far is we've just console logged things out. When we return, things get a little bit hairier. But if you're able to draw this out clearly in your head, if I just do a return here, well, remember, where does the function return something to?
Or whatever it's asked.
Right, whoever called it, right, whoever's called it. So if I have a return here, it means I have a return here. So if, let's say, countdown 0 gave me, let's say this was, instead of console logout done, this was return done. Where does countdown 0 return this done to? It returns it to here. And where does this guy return countdown done to? It returns it to here, right? You basically return each thing to wherever you called it from. This is something that I'm not going to spend too much time talking about because I could explain this for like 2 hours and it's not nearly going to be as valuable as you just doing the problem and probably hitting a wall at first and kind of working your way through it. But just keep in mind that a return, like because these three functions are all distinct, each function is going to return whatever value is going to return to wherever it was called or to whoever called it at the point at which they were called. That's like the main rule of thumb. Just keep that in mind when you work through these problems. Okay. So one last example problem we'll do is the factorial problem. Factorial is a math thing. Basically, it's just if I give you a number, it's just every number multiplied between 1 and that number. So 5 factorial is 5 times 4 times 3 times 2 times 1, and you can kind of work your way backwards. The only kind of edge scenario here is that 1 factorial is 1, 0 factorial is also 1. So once again, we can do this problem using for loops pretty simply, right? But the point of this is to practice using recursion. So let's see how that will look with recursion. We have a factorial number, right? Basically, with a factorial, what's like the mini problem we're solving here? Like, what's the core problem we're solving here? And the core problem we're solving here is the first step is figure out, okay, when do we go and when do we stop, right? When do we stop is the base case. And so the question is, when do we stop kind of multiplying more numbers? Well, if we look on the previous table here, right, when do we stop? Or when does it look like we stop?
When we get to 1.
Yeah, when we get to 1. Or let's just be a little more, like when we get to 0 or 1, right? Because there's no other process here. Like it's almost like we're just manually telling you, hey, when you hit 0, you're 1. When you hit 1, you're 1, right? Everything else, you multiply, you can calculate yourself out. But with 0, no calculation. You're just a 1. With a 1, no calculation. You're just a 1, right? So that's so usually when we see something like something like we tell you, hey, this is like your answer. It basically means we're gonna save you the trouble having to do computation. So it probably means you're done with this, like with this recursive function, right? So when num is 0 in this case, or num is equal to 1, you return 1, right? Because remember on the previous page, 0 factorial is equal to 1, 1 factorial is equal to 1. So when we hit 0 or we hit 1, we return 1. Any confused so far? So now, yeah, so basically, I mean, this is not recursion, right? Like we never call ourselves again. This is just like a straight up function,
yeah,
right? So we figured out when we stop, right? And it's pretty clear. We stop when num is 0 or num is 1, right? Like there's no ambiguity here. Like when I look, like this is how we should aspire recursive code to be. Someone looks at it, it's like, oh, clearly num is 0 or num is 0 or 1. That's when we stop. Cool. So the next question becomes, well, this is to prove that this works, which is a little bit redundant, but moving on now, when do we go, right? When do we kick off the next iteration of our loop? And so here's where the return gets a little bit more messy, because if we want to do result equals factorial of 2, what that is equal to is, well, so far we haven't written it yet, so we don't handle factorial of 2. But if we want to handle bigger numbers, what we're actually saying is, well, factorial of, if num equals 2, the factorial of 2 is just that number multiplied by what? Not just 1, but the factorial of 1, right? Because if we look, oh god, if we look here, right? 6 is equal to 3 multiplied by 2 multiplied by 1, right? So 3 is equal to 3, but 2 is equal to 2 multiplied by 1. So if we just replace this factorial of 2 here, this becomes 6 is equal to, 3 factorial is equal to 3 multiplied by factorial of 2, right? Because, 3 factorial, 3 times 2 times 1. 2 factorial is already 2 times 1. So 3 factorial is just 3 multiplied by factorial 2. 4 is just equal to 4 multiplied, 4 factorial is just equal to 4 multiplied by 3 times 2 times 1, which is also 3 factorial, right? So 4 factorial is equal to 4 multiplied by 3 factorial, right? 5 factorial is equal to 5 multiplied by 4 times 3 times 2 times 1, but we just said 4 times 3 times 2 times 1 is 4 factorial. So 5 factorial is just 5 multiplied by 4 factorial, right? So that's kind of the pattern we're looking at here. And so I'm just going to fast forward through this. Okay. So then if we want to actually do this problem, what we realize is, what we realize is the answer we're looking for really is just num, right? If I give you a number, the factorial of that number is just equal to that number multiplied by the factorial of 1 less than it, right? 5 factorial is equal to 5 multiplied by factorial of 5 minus 1, which is 4, right? 100 is equal to 100 multiplied by the factorial of 99. And so now we get to see not only our go scenario, but we get to see how, like, once again, we kind of almost like, if you can visually, like mentally put yourself, kind of pigeonhole yourself intentionally and say, hey, I don't care what number came before me. I don't really care what number came after me, right? All I care about is myself. So if you want to ask me what, let's say right now I'm 99, right? What value I give it? I'll say, hey, I'm 99 multiplied by factorial of 98. What's factorial of 98? The next guy will figure it out, right? The next iteration is going to figure it out. For now, I'm just saying that's what I am. And so because of that, what we're actually able to do is we're actually able to kind of create that same sequence of events where every function is it's either going to give you the answer, or it's going to say, hey, why don't you run this to figure out what the answer is, right? So if num equals 1, we'll say, hey, the answer is 1, and we're all done, right? No more like asking other folks. If we're 99, then we say, oh, why don't you let me run factorial of 98 for you, and let's figure out what factorial of 98 is, because I'm 99 multiplied by factorial of 98. I don't off the top of my head know what factorial of 98 is, so I'm going to create a function for you that's going to figure it out. And then when that person tells me what their answer is, I'll let you know what I'll be. Right? Yeah, Josh?
Is there like a universal limit of recursive function calls?
No. I mean, usually the limit is going to be your computer's memory, but
the reader won't stop it at a certain value, maybe.
No. I mean, you'll stop once your computer thinks you're throwing an error, like if you ran an infinite loop, or if your computer runs out of memory.
Yeah, like when would the JavaScript reader like say, oh, I think this is infinite loop, but really it's just too big?
Usually it's a function of your computer's memory.
Oh.
Okay. Yeah. Like safeguards are. I mean, it's almost like asking like, when does a website think like you're a bot, right? It's like everyone sets standards differently. Usually, like if you're doing real work, you almost never hit it. If you ever hit it, it probably means you're doing like really, really serious computation work, and those are usually done on special computers that have, like terabytes of RAM or something. So like it's not a concern that you need to have for any of the problems that we do today. Okay, cool. So yeah, so once again, right, my factorial function at this point is basically done. And I guess to answer Jake's question from earlier, notice how on line 8 is where we kind of call the next iteration of our function, right? But on line 9, we have another line of code that comes after it. And so if we were to run this function now, which we will in a second, if I was to run factorial 5, well, factorial 5, let's go through this now, right? How many, so well, before we say that, we'll say, let's run factorial 5. Our call stack is going to start at factorial 5. And we know that eventually we're going to be returning something called result. So what's result equal to? At this point, all we know is the result is equal to, because 5 is not 0 and it's not 1, we skip the if loop, right? And notice how even though we don't really have an else clause here, this is basically the else, right? If we hit our if, we return, and we're done with our function, right? So if we, by the time we get to line 6, it basically means our if clause was not met. And so it's almost implicitly saying, hey, this is your else condition, right? Another thing that's, once again, like I said, everything we learn is going to build up on top of one another. Notice how I was trying so hard to let you know that these are different functions. The other reason why is because of this return statement, right? If this returns something, this returns 0, for example, right? Once I hit return 0, does it kill these two functions? No. Each of these functions run independently of one another, right? So when this returns, return ends a function, right? But it only ends the current function it's in, right? So when this hits return 0, it's going to kill this function. It's going to give this value back to this function, but this function is going to keep running until either it hits its own return or it finishes the code, right? So with recursive functions, when you see a return statement, be very careful. When you see a return, it doesn't mean I'm killing every single chain in this recursive function. I'm just killing that iteration, right? I'm killing the function that I'm in at that moment. Okay? Once again, return ends functions. Just if you're comfortable with that, then this should be relatively straightforward. But if you're not, then you'll definitely get a lot of practice with it, right? So here what we're saying is the return value is going to be 5, or rather we're trying to figure out this result on line 7 there. And we know when I run factorial 5 is equal to 5 multiplied by factorial 4. Well, so in order for me to finish that line of code, in order for me to finish line 7 for factorial 5, I need to create a brand new factorial function where the input is going to be what? 4, right? So I've now added to my call stack. And once again, I'm adding to my call stack because factorial 5 cannot finish until we figure out what factorial 4 is, right? These things are not running in sequence, right? These things are dependent on one another. Or rather, factorial 5 is dependent on factorial 4. So I asked factorial 4, hey, what are you? And factorial 4 says, well, I'm not a 0 or a 1, right? So I can't give you back a number. But what I am now is I can tell you I am equal to 4 multiplied by factorial 3. So then I start another function called factorial 3, and this is going to keep going until I get to factorial of 1, right? So if I was to draw this out on the board, I would have 5 functions. There'll be 5 columns of functions running at this point, right? And finally, I get to factorial 1. And I say, okay, what are you? And he'll say, am I a 0 or a 1? Yeah, I am. Okay, cool, I'm a 1. And it's done, right? There's nothing else to run, right? For factorial 1, I returned a 1. It means my function terminates right there. I never hit lines 6, 7, or 8, right? So factorial 1 is going to return a 1. Everyone go so far? And then factorial 1 is finished, right? I've hit a return statement. There's nothing else for me to do, even if I wanted to. So then I go back and I say, well, by the way, who called factorial of 1 again? All right, we're in factorial 2, and factorial 2 says, hey, I'm 2 multiplied by factorial 1. So I call factorial 1, and factorial 1 says, oh, by the way, I'm a 1, right? So when we go to our statement here on the right-hand side, factorial 2 says, I'm 2 multiplied by factorial 1. Factorial 1 says, hey, I'm a 1. So now we can basically replace that factorial 1 with just a 1. And now factorial 2 says, oh, okay, great. I'm 2 times 1 now, right? I don't need to be dependent on any of the functions finishing. I have only numbers, right? I have values I can calculate myself. I'm just 2 times 1. So at that point, which line are we at on for factorial 2?
7.
We're at 7 still, right? Because we're still trying to figure out what result is, right? And now we know result is equal to num, which is 2, multiplied by factorial of 2 minus 1, which is 1. So we know 2 is 2, obviously. And factorial 1 is 1. So result is equal to what? 2, right? Do we return it on line 7? No. We then move on to the next line of code, line 8, and we say, oh yeah, whatever result was, let's give it back to whoever asked us for it initially. And so factorial of 2 is equal to 2 now. And by the way, who asked for factorial 2?
Factorial 3.
Right, line 7 in factorial 3 asks us, hey, I'm 3 myself, multiplied by factorial 2. And factorial 2 finally said, oh, I have my answer for you now. I'm a 2. And so factorial 3 said, okay, great. Let me slot that in now. For factorial 3, the result value is 2 times 3, which is 6. And then we go down this chain. Factorial 4 says, okay, great. That means I'm 4 times 6, which is my result value is 24. And then finally, factorial 5 says, oh, great. Factorial 4 is 24. I'm 5 multiplied by factorial 4. So I'm 5 multiply by 24, I get to 120. And then I hit line 8 for a factorial of 5, and I say I return result. And at that point, my call stack is what? Your call stack's not quite done yet, right? Because what's going to happen is factorial of 5 is going to return 120, and it's going to be stored where? In result on line 11 there. Okay, so we take off factorial of 5, but our function isn't quite done yet. This is a bit of a misnomer because after we finish line 11, our call stack is empty, but that just means what?
Go to the next line.
It means we go to the next line, right? And so we didn't show it here, right? Basically, console logs temporarily pops up on our call stack. We console log it out, and then we're done, right? So basically, it's like every single thing in JavaScript is going to take its turn, if you will, on your call stack. And it's going to run. For a console log, we don't show it because it's like super fast, right? It's almost like a straight like in and out process. With the function, obviously, there's different calls, so we put it on there. But just know that even though we've been talking about emptying our call stack, once our call stack goes to 0, it just means we now have permission to move on to our next line of code. It doesn't mean our entire page finishes at that moment. It means we now have permission to move on through our code. So yeah, so then on line 12, we find a console log out result, which is equal to factorial 5, which is 120, and now we get our answer. So once again, right, write your base case first, and usually the base case are pretty simple, right? Like when you start something, you should always kind of know like where, at what point you're going to be stopping. And then the other two are just kind of variations on the same idea, which is, hey, test with smaller inputs, right? If I'm trying to just figure out if my factorial function works correctly, don't test this factorial of 1,000, right? It's both like dumb, it'll take a long time, and it's really exhausting on your computer. Test this factorial of 3 or 4, right? Because guess what? You're like if you think about your function, like your breaking points are like 0 and 1, and then 2, right? Those are like kind of like the special values. Like if you look at your code, you treat factorial of 99 no differently than you treat factorial of 3, right? Like there's no special handlers for 3 versus 99 or any numbers in between, right? Your special handlers are at 0 and 1. So as long as you get that part right, like you kind of, once you test for like smaller inputs, usually larger inputs scale very nicely. Are you shaking your head because you don't agree, or?
Oh, no, I'm not shaking my head.
I'm just like. Okay, yeah. So normally we look at code, you try to figure out where your breaking points are. In this case for us, it was 0 and 1. So then we test kind of around there, and then we when we look at our code, there's nothing in our code that says we treat 1,000 any differently than we treat 1,000,000 or 10 million. Okay. So testing against smaller inputs, it's just a good rule of thumb for all testing, not just recursive testing. Yeah. So recursion, once again, right? Notice how like I didn't say, oh, we have a new function today, or we have a new keyword, or we have a new method, right? Recursion isn't a thing in itself. It's more of like a methodology. It's more of like a tactic. So this is, unlike scope or unlike pass by value versus pass by reference, you could probably never have to, you could avoid using recursion, right? You might be stumped by certain problems, but once again, it's more of generally speaking, it's more of a tactic that you use. And you can use it with anything, right? So, once you're comfortable with it, it's kind of like the for loop. Like once you're comfortable with the base idea of recursion, you realize that, hey, we can use it on strings, we can use it on numbers, we can use it on arrays, we can even use it on objects, right? We can use it on anything that we can really quote unquote measure. It's kind of like how I did my for loop for you on day 2. Is like it doesn't have to be like a number we iterate straight through. Right? I can use anything I want as long as my conditions are set up properly. So recursion is the same way. But for this morning workshop, we'll probably try to stay within more comfortable realms of like very easy to understand iterable things. Yeah. Cool. Start with the base case, test simply, and then always be clear with yourself, right? Don't lie to yourself and think, oh, like I'll just write this and hopefully the function is going to do the work for me. If you don't understand the mini problem you're solving, it means you need to do more thinking, not more typing. And then I guess if you're really stuck, try writing it iteratively, looking at it, and see if you can figure out what the pattern is. Right? Because if you can write it iteratively, it means everything you can do iteratively, there's probably a way to do recursively, but not vice versa. So if you can do it iteratively, it means there's definitely like a pattern you can use to figure out how to write something recursively.
Can you give an example of something you can do recursively you can't do iteratively?
That's this afternoon session. Yeah. Cool. Any questions? So once again, this morning's workshop problems will be more akin to what you see on the interview and the assessments. And usually how those go is they'll probably ask you to do a problem like iteratively and say, hey, like write a countdown function for me, right? And assuming assuming you're kind of like the typical student, you say, oh, great, the for loop does it really well, right? You write with the for loop, and then they'll ask like, oh, how do you do this recursively, right? And so it's less of like here's like a problem solved from a blind with recursion. It's more like, we kind of want to kind of build you up to it to kind of see where your level of proficiency breaks down, right? Ultimately, the point of the assessment is not to it's not like to say like you get X number of right, you're good to go, or you got X number wrong, like you fail. It's more like we want to figure out where you are, and so we'll kind of take you along a path, and if you fall along the path, at some point we'll kind of get a sense of where you are, right? So it's not like a binary, you either know it or you don't. It's like we'll take you along, and our goal is, once again, not to make sure you get it right or wrong, is to figure out where you are, like where your comfort level is with certain concepts. So that's kind of how it's going to look too. So when you work on these problems, like think about the process a lot more than thinking about getting the right answer. The right answer should be like the guide. It shouldn't be the means in of itself.